Welcome to episode 5, and our focus here would be to quickly look at Chatellier'S principle. We hope to have another episode which would help us consolidate the content, and then by episode 7 we want to do with full questions. All right, so we are going to look at what we call Chatellier'S principle quickly. And look, the idea, let me just quickly write this, the idea behind the principle. Before we state the principle, what is the idea behind the principle? All right. The idea is to maintain chemical equilibrium. If and when the system is disturbed. All right, so our system can be disturbed, and when it's disturbed, we need to maintain a state of chemical equilibrium. All right, the factors that disturbs the equilibrium position are: 1, concentration; 2, pressure; 3, temperature. All right, so these are the 3 factors that affect the equilibrium position. All right, so this is what a guy called Chatelier looked at. All right, and we're going to deal with this principle just now, Chatellier'S principle. Chatelier. This guy is my friend, and many people don't know that Chatelier is one of the board of directors of Krazifizix. Okay, and Chatelier lives in Cape Town. This guy is a Cape Townian. You know, I remember when we decided to name the principle, I said, no, go ahead, name it without me. I'll come in the future to name it. All right, I'll tell you why I said it's a Cape Townian just in a while. Now, this is what Chatelier said. He said, when the equilibrium when the equilibrium in a closed system, remember we've been talking about closed system, you can only reach equilibrium in a closed system, all right, is disturbed. And the disturbance can only come if there is a change in any of the 3, all right? It's disturbed by a change in a factor, okay? What happens? The system by itself, all right? So this is what the system does, and I'll try to use very vivid everyday picture to explain it to you. The system will reinstate. I wish I could really draw or do some cartoons for you. The system will reinstate a new equilibrium. The system will reinstate a new equilibrium by favoring. You need to know this, guys. You need to repeat this. This must be well known. You may not put this when you may not put that. All right, just explaining. All right, the system will reinstate an equilibrium by doing what? By favoring the reaction that will oppose the disturbance. By favoring the reaction that will oppose. I'll explain this whole story. You know, he told me in person. That's why I can explain it in different ways. All right. When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. All right. And what are the factors? The factors are simply what? All right. Please note, I want to repeat. The factors are concentration, pressure in terms of gases, how do you write Cape Town? The short form of Cape Town, CPT. I hope you got why I said this guy is from Cape Town. He's a Cape Townian, because the factors that affect him are actually the factors in Cape Town. All right, let me quickly do a demonstration for you of what I mean. All right, look at this. I've got a chair here. Good. It's a very simple demonstration. It's everyday thing. All right. And I have somebody sitting on the chair. Now, the person is sitting and this person is comfortable. Comfortable, I can actually say the person is in what? At a state of equilibrium. I know many of us would have idea of what I'm talking about now, because many of us in our schools have that kind of situation. All right. Now, if I were to ask somebody else to sit with this person on this chair, so I have somebody coming in from the side to sit with this person on this chair, what happens? This black guy will have to shift towards that side. Wait, that's the opposite. This guy is coming from the right. This person has to shift where? To the left. I've mentioned the one opposite. All right, the word opposite. And they will adjust onto a point where both of them are now comfortable again. So the change is not comfortable, right? But they will adjust until they find a new comfortable state. So there is a disturbance, but the system will behave in such a way that it will find a new spot of being what? Comfortable. That's what Chatellier'S is simply explaining. That if you change the concentration of a system that is at equilibrium, the equilibrium will shift to adjust to the change until we get to a new equilibrium. Same thing with pressure and same thing with temperature. All right. So this video is dedicated to looking at the three. So the first one, change in how will concentration affect equilibrium. So we're looking at concentration. Okay. All right. I wanted to see something here. Let's consider something first. A plus B. All right. This system is at equilibrium. Okay. How do I know? Look at my arrows. If the concentration of reactants increase, what happens? It means I have more reactants. Do you know what's going to happen? We need to use those extra number of moles as fast as possible in order to maintain a new equilibrium. All right. So if the concentration of the reactants increase, what happens? Equilibrium, remember it was stable before, will need to shift now. All right, to the right. That's number one. Should have actually labeled number one. Equilibrium will shift to the right. I'll get you to understand. Look at this state. This thing is balanced. If I put more of A, I have disturbed this thing. In order for it to balance, I need to form more products so that I use the reactants and balance it up again. So basically, look, this is what you're looking at. Let me try to do something here. Okay. So I have A plus B. Now, what happens? If I add more here, this thing now tilts this way. It's no longer stable. You know this seesaw thing that we play with, you know? It's no longer balanced. In order for me to balance it, what do I need? I need to move this guy All right? Can you see my arrow? I need to move this guy forward. The more I move this guy forward, the weight is now being distributed until I come back here again. I hope it makes sense. All right, so the forward reaction, this guy needs to go forward. The forward reaction will then be favored. I hope that explanation makes sense. All right. So let's go back to the note. If the concentration of the reactant is increased, what happens? Okay, I really don't like what I did here. Now, if the concentration of reactants is increased, one, equilibrium shifts to the right. Remember, our change is actually from the left. All right? The forward reaction is then favored. And what is the effect of that? More products are formed. Please note, Kc value remains the same. Kc value remains the same. A change in concentration does not affect Kc values. All right, good. What if, let's look at another scenario. What will happen if the concentration of the products increase? All right, number two. So let's call this number one. Okay, number two. If the concentration of products increase, what will happen? Now, my reactants are now very small. They're disturbed. What will happen? Equilibrium. And I want you to get used to the language. Equilibrium shifts where? To the left. Now, which reaction is then favored? Which reaction is favored? The reverse reaction is favored. And what happens? More reactants are formed. I hope it makes sense. I'm going to look at two more scenarios. Three. If concentration of reactants decrease, so we are now beginning to remove our reactants. Since it is less, it simply means, this means what we have. We have more what? Products now at first. What will happen? Equilibrium shifts to the left. All right? So that it can balance it. Equilibrium shifts to fill in what we took away. All right? Reverse reaction is favored. Now what happens? More reactants will be formed. And basically, if we were to do number 4, I'm sure you can fill up the gap now. All right? Number 4. If concentration of products decrease, this takes us back to the first one that we discussed. Number 4. What happens? Equilibrium shifts where? To the right. Forward reaction is favored. And more products are formed. All right. Remember, Kc value remains the same. I'm going to look at graphs as we go on. Let's quickly look at the effect of our second condition is pressure. All right, applicable to what? Gases. What will happen? How will pressure change the whole system? Number one, pressure changes, let's do this, with regard to volume. Remember Boyle's law, pressure is inversely proportional to the volume. So you would see examiners saying volume decreases. If volume decreases, it means pressure increases. All right. But what will a change in pressure do? Let me quickly explain that. So that you'll understand before I tell you. All right. Consider this reaction. Nitrogen gas plus hydrogen gas to give us ammonia gas. I want you to see something here quickly. All right. So I have a closed container. Let's use a red dot for nitrogen, and let's use a green dot for hydrogen. So I do have hydrogen. I want you to see, remember it's a gas, spatial distribution. All right. Okay. I could actually, let me make it nicer. All right. We said a green, right? No. Green. I need a circle. All right. Good. So I have nitrogen all over the place. Okay. Now this is hydrogen gas. Okay. Let's have some hydrogen gas. All right. It's actually nicer. So I have that. Good. Now let's have some ammonia formed. So it is ammonia. I'm just going to do this for ammonia. All right. So these ones have already reacted. So I'm going to have, okay, it's refusing. All right. But let me do this quickly because of time. So I have that ammonia there because it's NH3. All right. So we have a few that are formed, okay? And we have the other things that have not yet formed. We have this one's playing around, the whole thing. Good. Moving up and down. All right. So this is ammonia. This is nitrogen. And this is hydrogen. All right. If I were to press this thing down and increase pressure, what do you think will happen? You would notice that these particles, look at these three. Look at the distance now. You see they're quite far. But if I press this thing down and decrease the volume to half, what happens? My particles are now closer together. All right? It means that I will form ammonia easily. I will form ammonia easily because the particles are now closer together. The particles are now closer together because pressure is increased, volume has been decreased. All right, so I hope you got that concept. Now, this is what we say. All right. Increase in pressure. Increase in pressure. Okay. Favors the side with fewer number of moles but of gases. Very important. Fewer number of moles. So if you look at this reaction, look at this. N2 plus 3H2. Remember, this is homogeneous. All right. So if I increase pressure, which side will be favored? Okay, I want us to answer this question now. Increase in pressure for this particular one. what happens? Equilibrium here shifts to the right. Forward reaction is favored. And here we have more ammonia gas is what? Formed. All right, equilibrium will shift to the right. Why? It has fewer number of moles. And the opposite will be the case. If I were to decrease pressure, then equilibrium will shift to the left. Reverse reaction favored, and more nitrogen and hydrogen are produced. All right, so that's very straightforward. However, let me write this in red. If the number of moles are the same on both sides of the reaction, a change in pressure, whether increase or decrease, does not affect the position of equilibrium. I'll give you an example. Hydrogen gas plus iodine gas to give us 2 moles of hydrogen iodide. All right, if you check here, how many moles of gas do we have here? It's 1 mole plus 1 mole. That gives us 2. How many moles do we have here? 2. They are equal. Whether you increase pressure or you decrease pressure, it does not affect the equilibrium what? Shift. Okay, I hope that makes sense. Now, let's look at the third one. I've got 3 minutes, but I'm going to extend to about 5. Temperature. All right, let's quickly look at something. When we consider temperature, the average kinetic energy, all right, a reaction could either be exothermic or endothermic. Okay, this one releases what? Heat is, let me say, delta H is less than 0. Delta H is greater than 0. Here, releases what? Heat to the environment. This one does what? Absorbs. Okay, absorbs heat. Why does it absorb heat? I'm going to write something that will make you remember. It needs heat. All right. So, these are the things you need to look at. Delta H is less than 0. In fact, a reaction here could be written like this. Plus heat. It is exothermic. While this one could be written like this. A plus B plus heat. I wanted to see. All right. Here, heat energy is a product. Here, heat energy is a reactant. It's needed as a reactant. So these are the differences between the two. Okay. Consider A plus B, C plus D, delta H less than 0. All right. This here is always a representation of that reaction. So number one, it means that the forward reaction is exothermic. That's what it means. And if that's the case, it means the reverse reaction is endothermic. All right, that's how we read the stuff. So the forward reaction is exo because I'm given this. Okay. Please note, an increase in temperature always favors the endothermic reaction. Very important. Because it is endo that needs heat. All right. So if it needs heat and you give it what it wants, what happens? The reaction rate therefore increases. So that's a statement of fact. Increase in temperature will always favor the endothermic reaction, while a decrease in temperature will favor the exo. Please do not forget this. All right. However, we said earlier on, this is the only factor that affects Kc value. And the question is, how? Okay. Let's check something here. Now, A plus B, earlier on, we said delta H is less than what? 0. Which means it is what? Exothermic. Right. Now, let's increase temperature. Number 1, equilibrium will do what? Shift to where? Remember, increase in temperature favors the endo. So which one is the endo? This is my exo, remember, and this is what? Endo, because of this. So equilibrium will shift where? To the left. Number 2, what happens? Reverse reaction is favored because that's my endothermic. Okay? And what happens? More reactants are formed. What happens to Kc value? All right, remember, Kc is talking about product here. Okay, guys, we don't write this, and you would notice I've not written this all along. It's not a formula. We don't write this. But what do you notice? Do you notice that there's almost an indirect proportionality between them? All right. Since more reactants are formed, more, what would happen to Kc value? Kc value will what? Decrease, because now you are dividing with more. More reactants are formed, therefore Kc value does what? Decreases. I'll give you a question. I'll analyze a question for you just now. All right. Kc value decreases. Let's look at a case study quickly. Case study. All right. Consider this. X plus Y to give you 2. Okay, we said, I remember we used something earlier on. X2 plus Y2 to give us that, which looks like ammonia there. All right. Given that at 850 degrees Celsius, Kc is 1,2. When temperature, I'm just creating a question quickly, was increased, Kc value increased. Question: is the forward reaction exothermic or endothermic? endothermic. Lovely. Examiner is now throwing a thinking question at us. Given that at 850 Kc value is 1,2, when temperature was increased, Kc value increased. Very important. Is the forward reaction exo or endo? Let's answer this in a few seconds. Very straightforward. Number one, solution. What happened? Kc value, we're told, increased, right? Good. All right. And we're told that temperature was also what? Temperature was increased. Now I want to answer. I just wrote down the facts. Look at how I'm going to answer. An increase in temperature favors which reaction? Endothermic, right? That's a statement of fact. An increase in temperature will always favor the endothermic reaction, all right? For Kc value to increase, more products are formed. More products. Let me quickly explain that. Remember we said Kc, we're talking about that over that. Okay, so if this value increases, it means this value would increase. All right, and if this value decreases, it means this value will decrease. I hope it makes sense. Almost as they're directly proportional, but they're not. For Kc value to increase, more products are what? Formed. For more products to be formed, forward reaction must be favored. Forward reaction is favored. All right, I hope you're linking. Let's link it. An increase in temperature favors the endo. Statement of fact. For Kc value to increase, more products will be formed. I did that mathematics there for you. For products to be formed, it means the forward reaction is favored. Well done. An increase in temperature favors endo. The forward reaction is favored. Can we combine the two? An increase favors endo, and the forward reaction is favored. Can I then conclude that my forward reaction is endothermic? Conclusion. Forward reaction is endothermic. And you're done. That's how you answer such challenge. It's 4 marks. Just, guys, you'll notice I like writing in bullet forms. It's easy for you to answer your questions in that way. All right, so an increase in temperature. I want to believe that as we go through a few questions, we'll be able to answer questions like this, and we'll deal with full questions. All right, so please go over the video. Try to understand this particular part very well. I'm sure you've done the calculations. You have your 8 marks. We have about 7 or 8 marks again to grab from the general content. So go through the video again, rewind it, especially this Chatellier'S principle, this and the next one. In the next one, I'll be dealing with common ion effect, solubility, how to use your graphs, and all of that. Finally, I've really gone overboard. I've gone overboard here. All right. Catalyst, just a small note, does not affect equilibrium position because it speeds up both forward and reverse reaction simultaneously and at the same speed. All right, so both forward and reverse reaction are favored. So catalyst does not affect equilibrium position. Okay, catalyst does not affect equilibrium. But please don't forget, the only factor that affects equilibrium Kc value rather is temperature. Okay, so concentration, temperature, pressure affects what? Equilibrium position. Only temperature affects Kc value. This has been a wonderful session. Goodbye.